When we work within a mathematical space, we rely on sequences to lead us to specific points. But sometimes a space is broken. A sequence might cluster around a destination, only for us to find that the destination point doesn't actually exist in that space. Compare these. On the left, a sequence converges on a solid limit. On the right, a Cauchy sequence aims for a gap. This defines the rational number line. Following the sequence 1, 1.4, 1.414, it clusters at root 2, but there is no point there. Because the square root of 2 is irrational, the sequence falls through a hole in the space. To fix this, we have to build the missing points from scratch. We stop looking for the destination and instead use the behavior of the Cauchy sequences themselves to define the points. Theorem 1.6-2 provides the blueprint. It proves that any incomplete metric space can be embedded into a perfectly solid complete space, X hat. But we can't just say every sequence is a point. Different sequences can target the same hole. 0.9, 0.99 targets the same gap as 1.1, 1.01. We solve this by grouping every Cauchy sequence aiming for that specific gap into a single set. This is an equivalence class, and in our new space, this class is the point. To measure the distance between two of these new points, we look at the sequences inside them. We calculate the limit of the distance between their terms as they move further out. This calculation only works if we can guarantee that this limit of distances actually exists. Since these distances are real numbers, and the real number line is already complete, the sequence of distances is mathematically forced to settle at a solid value. By relying on the completeness of the real numbers, we've successfully defined both the new points and the distance between them. Next, we bring the original space into the new one. We map every original point to a constant sequence. The number 2 simply becomes a sequence of repeating 2's. This creates a subspace, W, that sits inside the new space like a fine, dense dust, ensuring the original structure is preserved. The final requirement is to prove the new space is actually complete. If we take a Cauchy sequence of these new equivalence classes, it must converge to a point that also lives in X hat. Because our original points are dense in this new space, we can always find a proxy point from that original dust that sits right next to each equivalence class. By lining up these proxy points, we create a master Cauchy sequence. This master sequence defines the final equivalence class where the whole process converges. The density of the original space provides the elements we need to prove the new abstract space is fully closed and complete. This completion is unique. You cannot build two structurally different versions of a completion for the same space. This is why the real numbers are the only valid completion of the rationals. To reconstruct a space, we identify gaps using Cauchy sequences, then define those gaps as equivalence classes. We use the limit of sequence distances to find the new metric, and use the density of original points to bridge the gap to completeness. Like, subscribe, and comment below on which theorem, proof, or textbook chapter you